Alright, so we're going to start our first lesson into Unit 3, and we're going to learn about something called the mole. This is a really important concept in chemistry, and it takes some time to really learn about what's going on, what the mole actually is. So don't worry if at the beginning it seems a little bit strange. Just keep practicing, keep trying out those problems, ask as many questions as you need to, and hopefully it'll get a little bit easier as we go. So, what is the mole? Most people hear of the mole and they think, well, I know that that's an animal. This is actually a picture of a mole. Some people think they're cute, some people think they're creepy, but they have a small little face and some big claws, but we're not actually going to talk about that mole today. So, the mole is actually a word that represents a quantity, an amount. So we're going to go over some quantities that you're familiar with first, and hopefully that'll tie in a little bit about the mole and relate a little bit more about what that means. So if I were to say you have a pair of something, like a pair of shoes, a pair of gloves, most people automatically think when they hear the word pair, it means two items of something. So a pair of shoes means you have two shoes. A pair of gloves means you have two gloves, and so on. Let's look at another quantity that's very familiar to you, a dozen. So dozen can mean a lot of different things to different items. It can mean a dozen eggs. That's very common. It could mean a dozen roses. Both of those are referring to 12 eggs or 12 roses. There's also a special type of dozen called a baker's dozen. Anyone familiar with that? If you've heard of baker's dozen, or if you haven't, it's really like a special type of dozen. It's 12 plus 1, so like a bonus, so you get really 13. So if you go to a baker and they give you a baker's dozen, you get 13 buns or 13 bagels. But if you hear the word dozen, most people think, okay, that's 12. Now here's one you may not be as familiar with, a ream. If you watch The Office or have been watching The Office on Netflix with some of your time off, you know that Dunder Mifflin makes paper, and paper companies sell paper in packages, and the packages are called reams. So everyone's probably familiar with seeing packages of office paper, but a ream represents 500 sheets of paper in this case. So it makes a lot more sense when we get into numbers that are a lot larger to have a quantity that represents a certain amount. It would be a lot harder to figure out, well, what does 50,000 sheets of paper represent? Or could we say how many reams of it? Can people imagine what 10 reams of paper, 10 packages of those paper, what that would look like or the size of it versus just throwing out a large number of sheets of paper? So that's where we're having some of these common quantities can come in handy. And the mole is also representing a quantity that we use in chemistry, but it's a little bit different. So we're going to come to that very shortly. Before we do, though, I'm going to try and give you an analogy here or a question to think about. Well, what happens in chemistry? What happens with chemists? What happens when you actually want to count things like atoms, molecules, ions? How do you even do that? They're so small, and think about how many of them could fit in a certain amount of something. Um, so let's take a typical sewing needle. Everyone's familiar with a sewing needle. And we want to try and guess how many atoms of iron are found in the head of the sewing needle. So the sewing needle head is this part up here where you put the thread through the hole. And to give you some kind of perspective in terms of mass, it's not a lot, 0.008 grams on an average size needle. So take a guess. How many atoms do you think are in there? Maybe make a couple of guesses. All right, let's check the answer. You probably haven't guessed it, but let's take a look. The answer is 80 quintillion atoms. If you don't know what a quintillion is, It's 8 times 10 to the 19, which when we write that out, the number looks like this. That's huge. It's probably a lot bigger than what you imagined or guessed. So, what do you think would happen if we tried to figure out how many atoms of iron were in a larger amount, like 100 kilograms? What if you were working in a factory or an industry where you're using large amounts of iron? How many atoms are in there? Would it be practical to count all of the atoms? Definitely not. Most calculators probably can't handle much higher than this. So chemists figured out a way and figured out a quantity to count things like atoms and molecules and ions instead of always just counting them individually. And that's called the mole. So, what quantity does the mole actually represent and what is it? Just like when we saw before, a pair means 2 items. A dozen means 12 items. Here, our mole is representing 6.02 times 10 to the 23 items. Now, you might think that's a very odd number and where it came from. We'll come back to that in a minute. We're not going to get into all of the details with it. Um, but it is how many items would be in 1 mole of anything. So to put that in perspective, because people are familiar with eggs, and they're a very hot commodity right now if you've been to the grocery store. If you were to buy 1 mole of eggs, that would mean you would have purchased 6.02 times 10 to the 23 eggs. Or if we expanded that all out, this is what it looks like here. That's a crazy amount of eggs. Now, obviously, eggs are a lot bigger than atoms, so using moles with eggs isn't really practical. But if we think back to our example with the iron in the needle, instead of writing out 80 quintillion atoms, we could use the mole to help us figure out how many items that might be and give us an easier number to look at. So where did the mole actually come from? It was figured out or talked about by a scientist back in the early 1800s, and his name was called Amadeo Avogadro. And we're not, again, going to get into all the details in this course about how it came about, but he found a way to relate the mass number of atoms using a unit called moles. And then later on, some scientists helped actually figure out a value of the mole. And because he was the first person to actually get into the idea of the mole and call it uh, the mole is also sometimes called Avogadro's constant. And we sometimes use the symbol with a capital N and a subscripted A to represent the mole, or 6.02 times 10 to the 23. So for us in general, if you just wanted it for quantity, 1 mole would be 6.02 times 10 to the 23 items. But since chemists use this, the items that we're interested in would be atoms. So 1 mole you could say is 6.02 times 10 to the 23 atoms. You could also say 1 mole is equal to 6.02 times 10 to the 23 molecules. Molecules, remember, are used for covalent compounds. And then 1 mole could also be 6.02 times 10 to the 23 formula units. And those you might not have heard of up to this point, but that's a unit that's used for ionic compounds. So at this point, what I want you to do is pause the video, and I've got a good clip in our D2L folder. I'll show you where it is. It looks like this one. How big is a mole? It's going to be under lesson 1. Pause our video, go in and watch this one, and then once you've watched that, come back to our lesson and we'll move on and do some more work with the mole and have your calculator out and handy. With the mole, we're going to do some calculating and converting between quantities and units. And we're going to use an approach called unit analysis. It's very versatile. You can use it in a lot of different places, but in chemistry, it's really cool. And especially if you're considering taking grade 12 chemistry and moving on and seeing more chemistry post-secondary, this is a great way to solve problems going forward. So I know we said we were going to deal with a mole, but to give you an idea of how unit analysis works, we're going to jump back to the idea with eggs and dozen because most people are very comfortable with that quantity. And then we'll try out some with our moles. So here's the question, and you probably can answer this very quickly. If you have 76,522 eggs, how many dozen do you have? So pause for a minute, pause the video, and see if you can calculate how many dozen that is. Okay, so if I were to ask you how you did that, most people probably would have said something like this. Well, I took my 76,522 and I divided it by 12. Did anyone do that? Probably. And you should have got 6,376.83 dozen. But did you do it with your units? Did you account for all of the ratios properly? Probably not. So, while most people can probably look at this question and get the answer, what we want to do is make sure we're accountable for all of the amounts that we're using with our units. So, let's look at our relationship here. Our quantity, we know 1 dozen is going to be equal to 12, and our items here are eggs. This is our ratio. You can write ratios a lot of different ways. You could say 1 dozen to 12 eggs. But another way you can write ratios in math is to write them as fractions. So I could also say 1 dozen for every 12 eggs. Or I could have it reversed. I could just flip the fraction. I could say for every 12 eggs, I will get 1 dozen. We're going to try and use one of these two ratios to use to solve our problem with unit analysis. So I want to actually show all my work, and I'm going to try and pick one of these two ratios to answer my question. So how would I do this? So I know this is the answer that I'm going to get, but how am I actually going to get there? So to show my work, I'm going to go my number of dozen of eggs, and I'm going to start off with the quantity that's always given in the question. So 76,522, and I'm going to put eggs with it. And then I'm going to multiply it by one of my two ratios. I can either pick 1 dozen over 12 eggs or 12 eggs over 1 dozen. And this is where that unit part comes in. See how I have eggs here up in the numerator? I want to make sure I can eliminate them. So in math, remember anything that's in your numerator and your denominator you can eliminate. I want to make sure that my unit of eggs goes in the denominator so I can cancel those units out. The other way you could think about setting up this fraction is, well, what am I trying to solve for? I'm trying to solve for dozen, so my units I'm solving for have to be on top. And I'm just going to shorten that because I ran out of room. So dozen. So looking at this, I don't have any numbers in yet, but which of these two ratios would fit in there? Dozen per 12 eggs or 12 eggs per dozen? If we look, our first fraction that we wrote out over here, our first ratio matches our units, dozen in the numerator and eggs in the denominator. Numerator, denominator. So now I can take my known quantity or ratio, 1 dozen and 12 eggs, And now I can solve for the problem the same way that many of you probably did right up here on top, but I've accounted for all of my units. So eggs in the numerator, eggs in the denominator, they're going to cancel out. And left with dozen, that's my units I want. And in your calculator, you're going to end up doing the same thing divided by 12, but how we would read this would be 76,522 times 1 divided by 12. And I'll know I'll be left with dozen. So you don't have to show this step, but that's what we're doing. And then you'll get the same answer, 6,376.83 dozen. So hopefully you've got a little bit of an idea of how we're going to use our units to solve problems. But now we're going to switch it up and try it out with the mole, because this is what we're trying to learn. So here's another example. How many atoms does a 2.6 mole sample of silver have? So this is what we're trying to solve for. How many atoms? We have 2.6 moles of silver, and we know the formula for silver is just Ag. The type of particle with silver is an atom. When we solve, there are variables that we use for each of these things, atoms and moles. So let's go through those first. How many atoms? We use a capital N here. This is going to tell us the particles. Here are type of particles we're trying to solve for atoms. So if I'm writing down my unknowns, my N is what I'm solving for, and I'm going to put in reference here my units, atoms. Then I'm going to look next. My next value I have here is moles. The units for moles, we just use MOL instead of MOLE. It's just abbreviated. Not much of a difference, but that's what we do. And the symbol that we use for moles is a lowercase n. Yes, I know there's lots of n's going on in here. So my number of moles is 2.6. And now we need a ratio, a quantity. And this one is where you can use Avogadro's number. So Avogadro's number, if you remember from a few slides back, is Na, and it's 6.02 times 10 to the 23 particles per mole. Here our particles are atoms, so we say atoms per mole. Or our ratio is 1 mole is equal to, or a ratio of 6.02 times 10 to the 23 atoms. So now let's try and solve the problem. These are our givens. We're just going to set these here aside. So if we're going to use our unit analysis method, we always set it up like this. What are we solving for? Our unknown. That's going to be n, our number of atoms. Then what comes next? Always a given measurement in the question. That in this case is 2.6 moles. And then we have to multiply it by our ratio, and we want it in fraction format. So again, there's two ways of looking at it. If I have moles in my numerator, I want to make sure moles from my ratio go in the denominator. That way they'll cancel. Or, and I'm looking at my unknown, which is atoms, my units on the top of the fraction have to be what I'm solving for. So I want to end up with atoms. So now I go to my ratio down here. And what am I going to put on the top and what am I going to put on the bottom? Well, 1 mole, I know moles need to go on the bottom. So 1 mole goes here. And my 6.02 times 10 to the 23 atoms has to go on the top. Now when we look at our units, moles and moles cancel, and we'll end up with atoms. Now, everyone should try this out in your calculator. I want you to pause the video and make sure that you can put this into the calculator. Sometimes when you're dealing with that scientific notation, 10 to the power of 23, you've got to make sure you put brackets around that number to protect it. Otherwise, some calculators do some weird order of operations. So pause the video, calculate your answer, and when you're ready to check, unpause. So let's check your answer. Hopefully you've tried. An unrounded answer would be 1.5652 times 10 to the 24 atoms. So hopefully you're able to get that answer, but we're not quite done yet. Hopefully you did a bit of review on significant digits, the previous lesson, and this is where it comes into play. So before we try out one more problem, what I want you to do is think about significant digits. If I'm going to round my answer here, how many significant digits do I need? So what you do is you go to the problem and you take a look and see any numbers that are given. The only number that's given here is 2.6. How many significant digits is that? Hopefully you recognize that's 2 significant digits. There are no other numbers given in the problem, and we never use our Avogadro's number to round for significant digits. So since this is the only value given in the question, and it's 2 significant digits, I'm multiplying and dividing here. When I round my answer down here, I need 2 significant digits. So I keep the 1, but I have to decide, do I keep the 5 as a 5 or am I going to round it up as a 6? When I look to its neighbor here, 6 is larger than 5, so I know this has to be rounded up. So it's going to be 1.6 times 10 to the 24 atoms. And that's my final answer with the correct number of significant digits. Here's one problem for you to try out. So what I want you to do is try part A. Part B is a little bit different, and we haven't tried that type of problem yet. So what I want you to do is pause the problem, try and see if you can answer part A. It's the same kind of calculation we just did in the previous example, and then we'll take that up and try part B together.